So first, let's recap on what we had in seminar 1. Okay, in seminar 1, we saw that the general problem of machine learning. So we have if we wanted to categorize everything in machine learning, we can have 3 different categories. The first category is supervised learning, unsupervised learning, and then something called reinforcement learning. Here, I'm mostly talking about supervised learning, but everything can be somehow translated into the area of reinforcement learning as well. But most of the concepts here are for supervised learning. So we have an unknown target concept. A concept is a mapping from set of inputs to set of outputs, could be your labels. And this concept C comes from some concept set. And then we have training examples that coming from some set M with some cardinality. Then we have, sorry, I guess that this is not the most updated version. Sorry, this is not the most updated version, I just updated the 5. Okay. Yeah, it's better. So I updated a little bit this diagram. So we have an unknown target concept that we want to learn, then we have a set of training examples, there is a learning algorithm, and then there is a hypothesis space. I will talk why we need to have another hypothesis space, not just considering the concept space. And then the combination of these two will work together to give us a final hypothesis. And the main idea here is that to have a function, a mapping that could be as close as possible with some definition of this closeness to somehow approximate the original concept C. So why we do need another hypothesis space, another space, not the space of these concepts, that could be very easily described here. Just consider that we have a set of labels, okay? And by the way, what is this concept C that I mentioned? It could be something here in high dimension, a very, very complicated figure it could be, that says that all the points inside here is +1, and all the points outside this guy is -1, okay? And now here, we have just 2 classes, class of positive samples and then negative samples, and this is the boundary of class 1, and this is class 2, okay? But we do need another set, let's say H, not C, here, because what we can do is that we can approximate this guy by a circle, and denote somehow representing this circle is much easier than representing this guy. The number of samples, for instance, that you need to find this circle is much lower than the number of samples that you need to learn this very crazy shape. That's why that in many situations you want to search over another hypothesis set, which is somehow a simplified version of this concept space or concept set. Again, but this is just one reason. We'll go to some other reasons as well. So this hypothesis space, for instance, it could be linear regression, for instance, perceptron model, or it could be a neural network. So different architectures of neural networks give you different kind of mappings. And over those mappings, you really will find the optimal mapping. So what is the role of a learning algorithm? Learning algorithm is essentially search over all the hypotheses here and then find the best one, defined by some notion of loss function. So you will define a loss function and then search over all hypotheses here, find the one that gives you the lowest loss. Okay? For perceptron model, for instance, the hypothesis space is the linear mapping, is a set of linear functions or linear mapping. So you have some weights that you want to find, and then this is your input, and then you will take the sign of this guy. And then the learning algorithm here is perceptron learning algorithm. For neural network, for instance, you have here the function space of neural network, and then for learning algorithm, you have backpropagation algorithm. For SVM, for instance, you have another function space, SVM function space, and here for learning algorithm, you have quadratic programming, for instance. By the way, I just forget that if you have some feedback here that controls how you will get some new training examples, so if you can somehow engineer the process of taking some new samples, usually it's called online learning. And of course, by having here, you can somehow modify this hypothesis space as well. Okay, but what you will see from now on, there is no feedback here, so you will not change the hypothesis space as you are going through the algorithms. Okay. So the setup of supervised learning that we will go from this setup is consider an input space X, some label space Y, and some unknown mapping, and the main idea is to find this unknown mapping from X to Y. We have a data set of m training samples, okay? And then these samples are given. So the main difference with online learning is that here we are not controlling how to take these training samples. Okay, so this is something given. We have the true output, which is y, which is c of x. So you have x, and then here is the mapping from x to y, right? From inputs to the label space. So here you have the true output. In this case, the true output looks like something like this. So you will put an x, and then this guy here says that if the output should be 1 or 0, and then you have a prediction of that output given by y that comes from some hypothesis space. Then we have a generative model. Usually, we don't need necessarily to have a generative model to develop an algorithm, but to analyze the performance of the algorithm, usually we do need to have a generative model. So what is the generative model? Again, something initially unknown. Is a probability measure on the product space of x and y that generates samples. So at the end of the day, what it says that the way that you create these training samples is not something engineered. It is something completely IID. So you're randomly taking samples from all over the space, not uniformly. It will determine by this p. But by some measure, you are taking samples, by some probability, you are taking samples from this product space. Okay? And then here, there is a very critical assumption that we do need to have for performance analysis. And this is that P, this probability measure, generates both the and future unseen data. So what does it mean? It means that whatever you want to say here, that you can characterize based on P, you can say exactly the same over here as well. So you don't need to deal with what should be the change of P from the data, from the way that you will take the samples and from your future data, okay? So everything clear so far? So it's just a setup, and then as we go on, then I will repeat some of those setups as required. Then we have a loss function, as I mentioned, which is a function, here you can see, which is a function of your input, x, the labels, c of x, actually the labeling function, and h of x, your approximation, okay? And this is very general formulation, so you can put anything here, and then you saw lots of different options that you can have here for different classification problems and regression problems. So you have a loss function here that measures how good h is for approximating c. Okay? Once the data are being generated based on this probability measure. Okay? And essentially you can define a risk which is somehow the average of the loss. Why you need to define this guy? Because at the end of the day you are taking just a few samples. Okay? And you don't know what should be the performance if you take the samples here and then if you change the data set to another data set, alright? Your performance will be changed. So in order somehow to bypass those changes, you can define a risk, which is essentially this expected value. Okay, so what do we have here? We have defined input space, label space, some mapping. We want to learn this mapping. And in order to be able to learn this mapping, we will define a risk. And ultimately, you will see that we want to somehow minimize this risk. This risk is the average loss that you can see. Okay? So this is the definition of the risk again here. So something that we should clear here is that the risk here you can see that it's not a function of the input, a function of your data set. Why is that? Because once you have your learning algorithm, you really don't care if your data set was D1 or if your data set was D2. At the end of the day, you want to apply this for unseen data, right? So the only thing that you care is the performance for unseen data, for test samples. If you consider NIID test samples, then this is the empirical average of the loss function. So you will fix, through some learning algorithm, you will find this H hypothesis. For all inputs, unseen samples, you will find this loss function, and then this is the empirical average. And then the point is that if the number of those samples goes to infinity, and if you have IID samples, then with central limit theorem, then this guy goes to that RL of P. And by the way, what is the meaning of RL and P? This is a function that will be characterized by these two. And what was L here? L is the loss function. And what is the P? P, actually that should be not capital P, a small case P. And this is the probability measure. Because at the end of the day, it really depends on how your data is being generated, right? So this is a function that will be parameterized by these two, as the input of this function is H, okay? So that's why that this objective function or this risk function is good, and we will work on that. Because at the end of the day, if you have sufficiently large number of test examples, your empirical average on the test examples will converge to this value here, okay? So if you try to minimize this guy, or let's say in practice you will try to minimize this guy, then if you have sufficiently large number of samples, you can somehow conclude that you are somehow minimizing this guy, roughly speaking, okay? So far we agree that this guy is good to be minimized. So then we can define a minimum risk, which is the infimum over all possible H. Here there is no limitation on what should be H. So this is a minimization over functional space of this risk function. And you can define the optimal hypothesis as the hypothesis that gives you the minimum possible risk for the test data. So now the first question is it possible to compute this guy? If we can compute this guy, then we can somehow compute this guy, right? So don't worry about computational complexity. I'm just now talking about if we can even compute this guy or not. Any idea? Actually, we can see the answer here. So the point is that we cannot compute this guy. Again, it should be a small case B, but we cannot compute this guy. So everything is very nice. We have some justification why we should work on that, but we cannot compute this guy. Why? Because what we can do is that we can evaluate this loss function for all the points in the data set for sure, right? So this is what we can do. You have your H. Again here, assume that H is given. So you are not optimizing over H. H is given. X and C of X for all the points in data set are given. So you have everything. You have the characterization of this loss function. So you can compute this parameter here for all the points in your data set. That's for sure. Okay. But for the points that are not in data set, you don't have this guy here. So you have this guy, but you don't have this guy. So you can't compute this guy for all the points outside your data set. Okay. But what you can do is that you can define somehow an approximation of this guy, or actually let's say an approximation of R. R as actually the average of this guy, right? So let's directly try to approximate this guy by saying that we will find the empirical average of this guy over our data set. What we have done here is that we didn't talk about the data set. We talked about all the space, right? And then we take the expectation over all possible X and Y that comes from the space, including those Ds and including all unseen samples. Here, we are just going for empirical average of the data sets that we do have. Okay, just assume that, just define, this is the definition, okay? You can do that. So we can compute this guy, this is empirical average. There is a very nice theory by Stone in 1977 that says that for consistent learning method, we will see later on what is the consistency, the meaning of this guy. But essentially it says that there is no error in the data set. Okay? So the loss in data set would be 0 for consistent learning method. For consistent learning method, this guy here will converge to that guy, which is a pretty strong result. So it says that, again, if we recall, we want to optimize this guy, we have justification to optimize this guy. What we will do in practice is we will optimize this guy. We'll try to optimize this guy, but in central limit theory, this guy will be that. And then we want to try to minimize this guy, but from this, what we can do is that we can replace this by that. We will see later on that we should not do that, but at least this theorem says that for consistent learning methods, okay, this guy here will converge to the true risk function, okay? And then there is there was no free lunch theorem in 1982 that says that, okay, that's a very nice result, but it won't say anything about the convergence rate. It just says that the convergence as m is the size of the data set. As the size of the data set increases, then we have this convergence in probability, but the other theorem says that there is no free lunch. So you can converge, but the rate could be arbitrarily small. So you would converge, but you would not happy with the convergence rate. Okay? Actually, the thing is that there are some probability distribution P, such that the convergence rate could be as small as smaller than what you want, and what you want could be anything, right? So it could be smaller than anything. So everything's clear here. Just to recap what we have here, this function is very good. We cannot compute that, but then we have an alternative to find this guy or approximate this guy using our data set. Okay. Yep.
We were talking about existence, but so if, I mean, in the end, if the convergence rate is slow, but it converges in the end to the optimal point at R star. So there exists still, but you said that that the existence of that problem, I mean, that R star doesn't exist.
No, actually there are two problems here. The first problem is that it says for consistent learning methods, first of all, it's a very big assumption. So it doesn't say that there are always consistent learning methods. It starts from consistent learning method by saying that if there is a consistent learning method, then for that consistent learning method, then we have this. Okay, and this result is very valid for like SVM, neural network, and all those things. It works. But then the problem is the convergence rate. So in order to be able to converge to this value, you may need to have infinite number of samples in your data set. So that is the main problem here. That you cannot work. And actually that's just one problem here. You will see in the next slide that while working with this is just horrible. You know, you should not work on that. But these two together will say that, okay, it's kind of good to work on that, but we should consider that there is no free lunch. So we should pay the price with the convergence rate. Okay. Here, so we have now the problem, the recap of the previous slide. So we have this optimization problem is actually these two optimization problem. Sorry. So we have a minimum risk here. This is the optimal risk. At the end, what was the risk? The risk was the expected loss that you can imagine, that you can observe for all the unseen data. And then this is the optimal policy. Sorry, this is the optimal hypothesis that you can consider. But then we know that we cannot compute this guy, at least mathematically. One good reason for that could be, in order to compute this guy, we need to take this integral, but then we don't know p a priori in many situations. So, for instance, you have some set of examples, some set of images, but you don't know the probability distribution. That the probability that maps, or this measure that maps the images to the shapes that you want to find, or the classes that you want to find in those images. So you don't know this probability measure in theory, but what you have is the samples from this distribution. And the samples from that distribution are your data set. Okay? So you have just some samples from that distribution, you don't have the distribution itself. That's why that you cannot compute this guy. But you can try to approximate this guy using your data set. Okay, so now one conclusion could be, using the Stone's out theorem, one conclusion could be, shall we go for this or not? So try to replace this guy here. So we have this optimization problem, try to replace this guy by its estimation obtained through D. And try to find the optimal H that minimizes this guy. Shall we go for this or not? And just to be clear, the definition of this guy is this. So this is the loss function, the empirical loss function that you can observe from all your points belong to your data set. Okay? Shall we go for this or not? Any idea? Can we solve this optimization problem first? So here the optimization is over all functional space. The thing is that, yes, we can solve this optimization problem extremely easily. That's very easy. What is a very easy solution for that? It's very easy, right? So you can always find, first of all, I'm not sure if I mentioned or not, but L, this loss function, is a mapping to some positive numbers, positive real numbers, okay? So the minimum of this guy could be 0, and then you can show that this could be always 0 if you always say that h of x is equal to c of x. Since you don't have any limitation on what h should be, you can do that always, right? So you can always say that this is kind of a distance measure, and distance measure between two identical values should be 0. So L of x of c of x and c of x should be 0 for sure, by definition.
But from before we don't know the function c, right?
You don't know the function c, but you know
the
c
value
of x of
yes.
y, right?
So how do you want to say that h is equal to c?
You don't need to say h is equal to c. The only thing you need is to say, you can characterize h in just some points. This is what is saying by this optimization problem, right? So you want just to minimize this guy, and I will tell you, I will give you one h that gives this guy, that makes this guy 0.
So
I can do that.
specific points only.
Absolutely, absolutely. You don't need to have even continuous function here, right? Because there is no limitation on the functional space. So that's very easy to see that you can always reach 0 here, right? Which you don't want, of course. But what was the problem here, actually? The problem is the huge functional space here, so you didn't have any limitation here. So you have extreme overfitting here. You really learn, and it just doesn't matter how many samples you put here. So even if d goes to infinity, well, it shouldn't go to infinity. But for finitely but huge size d, still you can just put h of xi is equal to c of xi, so that would be extreme overfitting. And that could be something like that. So here you have, this is your actual function that you have some point from. And then what h could be is something like that. It could be. It just needs to coincide with the actual function on those points that are in your data set, right? And any function, you can find infinite number of those functions here, right? And definitely you don't want that. Okay. So this is the problem of overfitting. And again, what was the problem? The problem is that the actual objective function should not be this. The actual objective function shouldn't have any d in itself. The actual objective is unseen data, but you want to somehow be able to generalize everything. And this is not the right way to generalize everything. So what you can say is that you can somehow put a limitation on something called capacity. We will measure that or say what is the exact definition of the capacity, but you put some capacity on your functional space. And if the capacity doesn't allow you to have these very crazy noise-like functions, then you cannot have this function here. Okay? So if you put some capacity, somehow it somehow measures how much expressive your function is, your class of functions h is. So this is somehow putting a limitation on the expressiveness of that functional space. And then now you are searching over those kind of functions with finite capacity. The problem here is that this h in general could be of infinite capacity, so it can learn anything, right? And at the end, it learns nothing for the generalization part. Okay, so we need to now define what is this capacity for different class of functions. Something more is we have this RLP of H. Let me erase something. So we have R of L and P. Let me write a little bit bigger. So we have R of L and P of H, and then we know what is the true value, the optimal value actually. Okay? So this is the absolute optimal value that you could achieve by the very first optimization problem here. If you could optimize over everything. And then the minimum thing for here would be 0, right? So what you can do is that you can write it down as R of L and P of H minus of R, L and P of H plus infimum of R, L and P of H over H minus R star. You can do that, right? I just add plus and minus of this guy. So now you can define these two as the first thing is this guy. Let's swing around. So just consider first this guy. This guy, you can call it approximation error. So the error that you introduce by reducing the capacity of your functional space. So it essentially says that, so okay, what is this? This is, it's not working. This is the best function in that functional space. This is the best function that you can do. And this is the optimal or the minimal risk that you can achieve, the minimal average loss that you can get using some functions in your functional space of finite capacity. So you can't get anything better. And what is this? This is exactly the same. What is this? This is the optimal thing that you could get if you didn't have any limitation on your optimization problem. So this is approximation error.
This R star is always 0.
Sorry?
R star, it's 0.
R star could be 0, but not.
You can always use this the C function and put it.
Not really. You can imagine some functions with non-zero R star, but it wouldn't change. So it just doesn't matter whatever the value of R star is. It just doesn't change the story, right?
But I was wondering, for example, if you put C,
Okay.
you put that inside this RLP, then you get 0, isn't it?
Where should I put? Yeah, RLP of C should be 0. That should be 0.
So
Exactly.
if you have no constraints on H, then you can always put C in.
Yes, you can put C, but then the problem is that you don't know what C is.
Yeah, but this is just like but you know that it's if it exists. I mean,
Yes.
if you know that there's a C, then you can always plug it in. And
Exactly, exactly. But if it allows, if it's somehow, let me see. What you are saying is true. So we can say that if there is absolutely no limitation of this guy, then we can achieve 0 risk function. Okay, but you may have some constraint on that. Okay, and if you have some constraint on that, just by saying that, for instance, H should not be the class of C. So C should not be in the very big class of H. Okay, so you are allowed to use any H with infinite capacity, but that H should not contain class of C. So you can consider this. Again, that would fall in this category. At the end of the day, even if R star is 0, it wouldn't change these two types of error. Then you just need to put this guy 0. Right? So you have an approximation error which is the price of reducing your capacity, the expressiveness of a functional space. So you can change, you can improve that at all by adding more samples at all. So this is a fundamental limit. In order to improve that, you need to make your functional space more complex or more expressive. So you need to somehow work on this H, cal H. And there is the second term, which is this term, estimation error. So this is the loss that you have, and this is the optimal loss that you can have in your functional space. Okay? And this is something that you can work on. And you can have more and more samples so as to improve this guy. Okay? So what is the PAC learning framework? It is first defined classification problem, but then you can extend everything to the regression problem as well. But for the classification problem, and usually for two labels, 0 and 1, so binary classification problem, the original problem that it proposed for. Mainly actually the VC dimension is proposed for that setup. But in any case, consider classification problem, again, input space X, variable space Y, unknown concept here, and unknown probability measure on XY that generates your sample, and then you have a data set. So don't worry about the noise in the classification, the fact that you can have some misclassified thing, some error in your data set or not. So far, for everything here, you don't have this guy, so you have noise-free classification. And noise-free data set as well. So when we are talking about complexity, we are talking about two different things of complexity. The first one is the sample complexity, so as to reduce the estimation error. Okay? So how many training examples are sufficient to learn a target function? So first of all, here we should define what is the learnability, and then once we define that, so how we say that, what is the definition of learning a function, okay? But once we define that, then how many training examples are required to achieve that definition? And then we have the model complexity, which says that shall we work on cal H, on H space to add more and more expressiveness or more and more capacity to that hypothesis class or not? Okay. We will come back to this slide later on, okay? Don't worry about that. Some definitions that you need actually you need them to prove the PAC learning framework part. Consistent hypothesis, which is a hypothesis in your class of hypothesis, that we will say that this hypothesis is consistent with data set if it produces no error. Okay, with any measure of your error or any measure of that loss function. So if it produces 0 loss, then we will call this a consistent hypothesis. Second definition, version space, which is a set of all consistent hypotheses. Okay, so here consider that this is hypothesis 1, this is hypothesis 2, this is hypothesis 3. None of them are consistent hypothesis. Why? For instance, if you consider these two, this is the class and this is the hypothesis, and is it a consistent hypothesis? No. Why? Because there are some samples in this class here that can't be covered by H. Okay? So that's why that all the samples, if we increase the number of samples, there is a possibility that there are something here that can't be covered here. And that's somehow the meaning of inconsistent hypothesis. The set of all consistent hypotheses is called version space, okay? And then definition 3 that we saw already, I guess, this is the true error. So this is the misclassification error over future data, okay? Here, now Okay, what is the definition of misclassification? So far we had the loss function, but misclassification is just mapping from your points to plus and minus. So the loss function is actually plus and minus 1. So plus 1, or it could be plus 1 and 0. So you will have a loss if h of x at some point x is, if h of x is not equal to c of x. If so, then you have a loss function. This is somehow called a symmetric difference of two sets. In this case, it's here and there. These two areas are actually this guy here. And the probability is the probability of having some samples here or there. So this is the probability of having this guy here. So this is a kind of loss function that we have here. Okay? So far clear? Everything? Simple. Okay, first of all, the first question is, can we learn the right concept? Can we learn this guy using a finite number of samples? Or even infinite number of samples? By learning, I mean, is it possible to tell me exactly what is c of x for some unseen future x? Of course you can't, because it's always possible for me to find some x outside that D, which is your data set, and then you can have some error on that very specific samples, right? So this is always possible. That's why that we can really learn the right concept. Now, what about a good approximation of the concept? So you let some error happens, some non-zero error happens, you're okay with that, but is it possible to have a learning algorithm that allows you to learn the actual function, the actual C with some error? Again, not. Because again, I can't give you an example that give you some error more than that. The only thing that you can say is having with something, some statement with two kind of uncertainty, which is the PAC kind of learning thing. So you can have a good approximation of the actual concept with some probability. This is what you can say. So at the end of the day, you can say that this is the error, and this is the probability of having error. So what I wanted to say in the first one is that you can't have this error to 0 for all unseen h. You can't make sure that this is something that can happen. And then the second statement is that you can't make sure that this guy is deterministically happening. What you can say is that you can say that this event is happening with high probability. This is what you can say. And this is the statement of PAC. So it says that the probability of having loss more than epsilon is smaller than some delta. So with probability 1 minus delta, you will be happy. This is the definition of your happiness. So you will be happy with your h. And if there is some h, if there is an algorithm, so here you need to have a statement efficient as well. So if you can find in an efficient way, we will go on to the definition of efficiency here, but if there is an efficient learning algorithm that makes this happen, then you are happy with that, and then you are saying that this algorithm is PAC learnable. It's a PAC learnable algorithm.
So the sample complexity, how it relates to this?
This is exactly this efficient algorithm. So the efficiency is something like that. The algorithm should be polynomial in 1 epsilon and 1 delta. If the algorithm is polynomial in 1 epsilon and 1 delta, then you can call it PAC algorithm. And what is the sample complexity? In order to have this guy, you will see later on the exact equations, but just to get some insight, this is the error that you can have, and once you have more and more and more samples in your data, then you can have a better representation of age compared to, so you can reduce this guy, right? By having more and more and more samples. So you can reduce this probability, so because you can improve your age. So this is the way that sample complexity comes to the picture. So if you increase the number of samples, then you can reduce this error and make it smaller than delta. And then you will be happy. So then you are in the PAC learning regime.
What was the triangle?
Triangle is a symmetric difference of two sets. So the triangle is actually this event. So this is the difference. So in this case, this is the area, and this is just a notation here. But just consider that this is a loss function here, so you can just put a loss function here as well. So this is the probability of having your loss function greater than epsilon. Everything should be smaller than delta. And for classification problem, this loss function can be defined as misclassification here. Okay? Okay, for finite hypothesis classes, you can have two different hypothesis classes, finite and infinite. Just to give you an example of infinite, for instance, the set of linear assume that H of X is W transpose X, and then your classification algorithm is perceptron model which says that take sign this is the mapping, and then take sign of W transpose X. And then if it is positive, say the label is 0, label is 1, and if it is negative, say that the label is 0. So binary classification, very easy one. This is, what is the dimension of the hypothesis here, hypothesis class? The hypothesis class is parameterized by W, and W can be anything in real numbers, right? And here, it depends on the number of features. So if X comes from some R with D dimension, then W comes from some other R with D dimension, right? So definitely the dimension of this capital H is infinite, right? Because it can be anything in the dimension. Okay. Do you follow? Everything is easy. Okay. In this case, everything that we will say here will collapse. You will see why. Okay. Theorem 1. If C is in H, so if it is a consistent algorithm, consistent learning algorithm, so it says that somehow C, or you're lucky that C is in your hypothesis class. If so, then the probability that you find a learning algorithm that it is PAC learnable is this guy. So actually, let's say, then for any epsilon between 0 and 1, this is the tolerance of your error, the probability that version space contain, I will try to somehow decode these words, but the probability that version space contain a hypothesis with error greater than epsilon is less than S. So it says that this is your delta, kind of delta, this is your epsilon, and version space contains a hypothesis with error greater than epsilon, which means that version space contains, okay, we will come back to the version space, but version space was the space of hypothesis with no error in your data set. Okay? So it says that the probability of having a function here that gives you error greater than epsilon is smaller than this value here, where H is the dimension of, or the cardinality of the set of your hypothesis, and M is the number of samples. So now we are happy with this. Are we happy with this or not? This is good because this error will exponentially reduce by the number of samples. This is very nice. But then you have a linear increase with H. And in this very specific class, it will collapse, right? Because here you have infinity here. And it just doesn't matter how many samples you are injecting. This bound is not a right bound, actually. Okay, but to see why it is the case, so essentially what it says is actually decoded here. So any hypothesis in version space, again the set of all hypotheses with no error in data set or consistent, it says that any hypothesis that is consistent with a lot of data means that you are increasing M. If you increase M, you are increasing the size of your data set. Okay? And if you are still consistent, it means that if your hypothesis gives you no error in all your data, and if you still increase the size of your data set, still the hypothesis gives you no error, then the probability that this gives you error in some other unseen data will be reduced by, will be less than this guy here. So it says that a hypothesis that is consistent with many training examples is unlikely to be seriously wrong. So this is what it says. Unlikely means that the probability of being seriously wrong is less than that guy. So then we will say that this is PAC. Okay? Probably approximately correct. Okay, and the proof is very simple. So first of all, you should find the probability that one unacceptable hypothesis agrees with data set. And then since the data set individual sample, you have this probability of having error. Okay? And then you have M samples, and then samples, you can assume that they are IID. Then the probability that you have unacceptable hypothesis is 1 minus epsilon to power m, and then you can use this inequality, so you have this guy here, and then you can use union bound for this guy. So this is for individual hypothesis, and for all hypotheses in your version space, you should have this. So at the end of the day, you have something like that. You have k e to power minus epsilon m, and then k is smaller than. What is k? K is the number of consistent hypotheses. And the number of consistent hypotheses is for sure smaller, or it is up to the number of all hypotheses, right? So that is the way that you can get this one. This one. Again, this is a nice result, but then the problem is that this is valid only for finite h. And then since we are using union bound to find this guy, the bound is getting extremely loose once you increase the number of those summations, those k. So once k is increasing and increasing and increasing, your bound would be looser and looser and looser. Okay? So at the end of the day, for large hypothesis space, this bound is not tight. But this is something that still you can call it PAC. Okay? The second theorem is much better. It's still not tight, but much better, because it's agnostic learning. So the second bound, it doesn't need to have C belong to H. So it says that for all learning algorithms, what we can say is that the same result, but here we have 2h e to power minus 2 epsilon. The price of not assuming that C belongs to H is here. So we have a 2 here, we have epsilon 2 here, and a 2 here. 2 here just doesn't matter. This epsilon square is much more important, the impact of that guy. Okay, so in order to prove that, what you can say is that here the proof is not that much easy, but still it's very easy actually. So here you need to use Houghton inequality, which says that for a set of IID Bernoulli random variables, you have this inequality. So this is something given for you. Okay? What you can do is that you can define Zj as a Bernoulli random variable, which is 1 if for some variable j, h of I of xj. What is h of I? This is your hypothesis I belong to some class of hypotheses, okay? The class of linear mappings, for instance, with finite cardinality, of course. But h of I at some points like xj, some samples like xj, if this agrees with Cj, then say Zj of 0, otherwise Zj is 1. So it's a Bernoulli random variable. And then you can define an empirical error, which was again your loss. You can recall that. You can define your empirical error as that. So this is the error over your data set of size m. And then you can define the true error, expected value of that variable. Okay? So everything is pretty much like the first slides. Okay, and then you can use Houghton inequality for this z of j. Yes, you can define that for z of j's. And then you have this bound, and then again you can use union bound again. So find the worst case scenario. So focus, this is true for individual hi, and then you want to make sure that there is no hypothesis in your class of all hypotheses in your H that violate PAC learnability, because you want to make sure that what is the performance of your worst algorithm in that class. So that is actually the main reason why everything here would be very, very loose, because here you would consider the worst case. So here you would put the maximum of this error, and the maximum of this error is larger than all those errors, and then you can find this guy. You can bound this guy by summation of all those errors, actually. And if so, if this is true, then you can say that this is uniformly learnable. Why uniformly? Because two things. The first thing is that it doesn't depend on individual HI, so this is valid for all H. Okay, so you are not saying that this bound is valid for just one thing in your hypothesis, for individual HI. This is valid for all hypothesis space. And then this is uniformly learnable for all probability measures. Okay, and these are two main reasons why this bound is very loose. But again, you have this bound here. Okay, again it will collapse if this dimension goes infinite. And then from those bounds, you can simply find the sample complexity, right? For instance, the first sample complexity is very easy. You just set e to power minus epsilon n less than delta, and then from that you can end up to the first bound, which is m of epsilon and delta should be larger than 1 over epsilon log of h divided by delta. So then you can see that this is a polynomial of epsilon and even a log polynomial of delta, 1 over delta. And that's why it's called PAC learnable algorithm. Again, everything will collapse when the dimension here goes to infinity and the bound is not tight. Still, they are PAC learnable, but the bounds are not tight. The same thing for ecosystem hypothesis. Okay, and then now you can bound the true error actually. So if you solve the same equation here, this equation, for instance, for epsilon here instead of m, then what you can have is that, and you just assume that H star is a hypothesis with minimal true error. So I guess I remove, but that is the best that you can have actually. Okay. Then you need to use this inequality here twice, and if you use that twice, then you will end up to something like that. So for any H in your hypothesis, the error that you can get in your hypothesis is smaller than something we call approximation error. So this is a DC of your error. You can't do anything better than that, which is due to your hypothesis, finite hypothesis dimension. And then there is an estimation error, which goes to 0 as m goes to infinity. Okay. Any question so far? So nothing is magic, just simple math here. Everything gets more interesting once this guy goes to infinity, actually.
So maybe I missed some part, but all these results are derived for asymptotic case, like n tending to infinity.
Yes, absolutely. Nothing is for finite n. And actually you can see that for finite n, these bounds just doesn't make sense at all. So, because most of them are coming, for instance, here they are coming from Hofting inequality that is tight for large n, for small n it's not tight at all. So for a small dimensions, a small number of samples, you can say anything.
Okay.
So what's happening for infinite hypothesis class? Which is probably you know already everything in finite hypothesis class, but for infinite hypothesis class, first we need some new definitions. I'm gonna need board actually to define them. So crazy, very hard to understand definition, but not that much hard. The first thing is shattering. So let me just read the definition here. So given a non-empty concept class C that belongs to a power set of X, your input space, and a data set D, a subset of, again, input space, define by this notation the set of all subsets that can be obtained by intersecting D with a concept in C. Okay? And then if this set contains all possible subsets of D, then we will say that this D is shattered by C. Okay, I guess that it was very hard. So let's try to find to apply that definition on these two examples. What's the first example? X is the set of real lines and C be the set of all intervals. And we want to see if C can shatter a set of 2 points or not, and then a set of 3 points or not. So the first example is X is real line. This is your X. And C is the set of all intervals. Let's, for sake of simplicity, assume that instead of C, this is H. Okay, so your hypothesis is a set of all intervals open or closed on X, and then can we shatter a set of 2 points or not? So just consider that this is my 2 point, and C or H is intervals. And by saying that, we can, for instance, say that everything inside interval, we will say positive, outside, we will say negative. Okay, so this is my concept. And then this interval can be, you can change the size of this interval, it can be open or closed. Okay? And then we have 2 points with any possible labeling that you can imagine.
Move around so much. Just stay over there.
Okay.
Yeah, stay close
so
to.
Then you can assume that any possible labeling here, we will say that these, we will say that this interval class, this class will shatter the set of 2 points here if for all possible labelings that you can assign to these 2 points, there is an interval, okay, that makes that labeling happen. For this example, it will be like that. So just to make an example, assume that we have minus and minus. So I can define my interval like that, right? Sorry, I can define, so just imagine that this is plus and plus. I can define my interval like that, right? So if so, then by this definition, then I can shatter this. Shatter, I mean that I can classify this correctly. I can have 0 error in these two, okay? So then what would happen if we have plus plus minus plus? I can define my thing here. So my class, I can define it here, or my hypothesis. So as to say, I can define it here, and then it will correctly classify these two. What would happen if you have plus minus? I can define it here. And what would happen if you have minus minus? I can just change the definition here. So say inside interval minus, outside plus, and then define here my set. So this is I can do, right? So all possible labelings can be covered by this hypothesis class. So if so, then we will say that this C will shatter a set of 2 points. So this is the definition of shattering. So this is what these sentences are trying to say. So for any set of examples that you give me, okay, and actually for one set of examples and any possible labelings, if I can classify them correctly with no error, then I can shatter them. This is the meaning of shattering. So what about set of 3 points here? So again, C is interval, but now we are talking about the set of 3 points. So by 3 point, here we add another point. If all the points are positive, then the interval is like that, right? So we can consider, we can correctly classify them. If the points are all negative, we can do that. If we have this, we can define this, right? If the points are minus, minus, plus, still we can. But what about this example? Can we classify this correctly? No. Or can we classify this? Minus, plus, minus? Again, no. Because in order to be able to do that, we need to define something here, and then something here. We can't limit ourselves to this. So that's why that we can't shatter a set of 3 points. So now let's consider another example in 2 dimensions. Let me delete this one. In 2 dimensions, and let's consider 3 points. Plus. So these are our 3 points, and I want to see that if the concept of linear separators here can shatter any set of 3 points or not. So, is it possible? So in order to say that, we should see that for all possible labelings that you can assign to this, is it possible to find a separator in that class that can correctly classify them or not? So if you put positive, 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 then I'm saying that this is my separator and everything here is positive, everything here is negative, right? So I can correctly classify that. My hypothesis space allows me to do this correct classification. So this is what it's trying to say. What about positive, positive, negative? Yes, I can define this. So again, the hypothesis space allows me to do that. So these are inside the capacity of my hypothesis space. This is what this guy is trying to say. Now, what about the set? And then you can consider all other configuration, and then you will see that you can shatter them. So you can shatter a class of 3 points. But what about the class of 4 points? A data set of 4 points. If they are positive, 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 I don't know, negative, then you can consider line like this, right? So you can consider this. But what about this example? So there are examples of 4 samples that you can correctly classify with no error. But what about this example? Is there any hypothesis in the class of linear separators that can correctly classify this example? By correctly classifying means gives no error here. It's not possible. Because if you want to be able to classify these two, then you should have a line either here or there. Right? And if you have a line either here or there, then you will miss either classifying this guy or classifying that guy. So you can easily show that it's not possible to find any hypothesis, just one hypothesis. Here you have 2 lines, you should have just 1 line, right? So it's not possible to find any linear separator that gives 0 error here. So what does that say? It says that the class of linear separators are not able, fundamentally, they are not able to classify 4 points with no error. So this is the definition of the capacity. So in that case, if you want to say what is the capacity of the class of linear separators, then you can say the capacity is 3. By the definition of the capacity as the maximum number of points that you can shatter, the maximum number of points that you can always correctly classify. So this is the actual definition here you will see. So the examples were clear. So here you will see the VC dimension, the Vapnik dimension. So the VC dimension of H is the cardinality of the largest finite set of points. In that case, it was 3. The finite set, the largest finite set of points that is shattered by H. So essentially, if you tell me that the VC dimension of some hypothesis is D, I can say you, for finite D, I can tell you that for any possible configuration of D points in your X, there is a hypothesis in H that gives you no estimation, no classification error. So this is inside your capacity. Your estimator can really estimate, your approximator H can really approximate that with error, with no error. Okay? This is much better than cardinality of H. Why? Because the cardinality of the set of these linear separator are just infinity, right? Whereas here the capacity of these guys are just 3. So that is the main novelty here actually. So what is the difference between two different classes in this setting? This is a hypothesis with very small VC dimension, and this is a hypothesis with, or hypothesis class. Actually, this figure, very ugly figure, comes from a hypothesis class, very complicated hypothesis class, a hypothesis class with a very high capacity. Why? Because it can really classify with no error over very complicated concepts. Here it's not possible for this guy to do that. Why? Because the capacity of this guy is 3. So it can classify with no error over only 3 points. If you go for 4 points, there are possibilities that this guy will fail. Here, if the capacity of this guy is, I don't know, 1,000, just consider that, then there is some hypothesis in that class that can correctly classify for any 1,000 points that you can imagine. Now, if I come back to the very original problem, here it was, okay, if I want to solve this, what should be the maximum required dimension of hypothesis here? It should be m, right? If it is m, then for any m, I can go for error, 0 error here, by definition. By definition of VC dimension, there is some h in that class that can classify m points with no error. And with no error, it means that this loss will be 0. So the only requirement is that VC dimension here should be m. Okay? Clear? Okay. And then some examples that you see, for instance, here, for linear separators, on 2D plane, then this VC dimension is 3. In ND plane, you can say that this would be n plus 1, actually, you can show that. There are actually lots of works on that, because this really shows the capacity of this class of hypotheses. For instance, I know that there are also some works by neural network, or simpler version of this, very simple version of neural network, somehow to characterize the capacity of this class of hypotheses, the capacity of the neural network, how much it can express some functions, something like that. You can easily show that the VC dimension for finite hypothesis is less than this. It's very easy to show. And then, why it is good? Because if you now have some bounds based on VC dimension, you can see that the VC dimension is much smaller, usually much smaller than the cardinality of the set of hypotheses. So for finite hypothesis, everything was a function of h, not a function of log of h, right? Log of cardinality of h. And now if something depends on VC of h, then you can see that this bound is much tighter than this bound. The bound that will be derived based on this guy, okay? Again, this problem here, everything here, tries to say what should be the correct complexity of your hypothesis class, okay? And once you figure it out, then the second question would be what should be the sample complexity, how many samples you need to have a PAC learnable algorithm. Okay? Let me see. Okay, this is like a free lunch theorem. You can find something like that. Just extension of whatever we had previously. Okay, this is another thing that you can show. M is the number of samples. So once you fix the VC dimension, somehow the complexity, the capacity of your hypothesis, once you fix that, then M, the number of samples that you need, usually, not always, but usually scale with the dimension of the hypothesis, not the dimension of this guy. Actually, the dimension of the hypothesis doesn't need to be this guy anymore. The dimension of the hypothesis is actually this guy. This is much tighter dimension for that guy. And it will be usually linear in that VC dimension. And then if one hypothesis is a subset of the other one, and their VC dimensions follow this inequality. You need this to prove this. And this is something called fundamental theorem of statistical learning, which says that the hypothesis H is PAC learnable if and only if the VC dimension of H is finite. So for any hypothesis of finite dimension, then this hypothesis class is PAC learnable. Namely, there is some algorithm there that gives you that PAC definition with polynomial in 1 over epsilon and 1 over delta. There should be some delta. I guess that this one was delta. I mistakenly put epsilon here. Okay? So you remember the definition of PAC learnability. This says that the only thing that you need to be worried is not the actual dimension of the class, is the hypothesis space, is the VC dimension of that hypothesis space. And the proof is not that much easy, but not hard actually. So you need to have these 3 steps actually. The first is a very, very well-known lemma that you can use, and then the second thing is that you should use the uniform convergence of actually having a finite VC dimension automatically implies uniform convergence for all H inside that hypothesis class with this definition of uniform convergence, and once you have done, then everything is fine. Okay? We can talk about it offline. I guess that we don't have that much time to go through this because there's something that I want to talk at the end of these slides. So then we can show for sample complexity, so the same results as finite one here. For consistent hypothesis, again the hypothesis that makes no error on your data set, we can show this, and D is the hypothesis, this is the VC dimension, much smaller than cardinality of H. Okay? For inconsistent hypothesis, the hypothesis that allows some error, so this is an extension of the original work of Vapnik, which says that if you allow some error, then the error that you can have, and the true error that you can, this is the true error that you have, and this is the empirical error that you can get. The empirical error is less than the true error plus some function of m, some decreasing function of m. Okay? And then you can see that this is almost linear function of D, as I mentioned earlier, which is not the case for all hypotheses or space and all the problems, but you can see. Again, the bound is not that much that I should tell you, because everything is based on uniform convergence, and uniform convergence means that you should tell that this is true for all possible H, and since you want to tell that this is possible for all possible H, then you should have a union bound, and then everything is not that much tight again. But still, it shows PAC learnability, and you're fine with that. So any question? No? Everything was not clear? Okay. So some extension you can have on that. So there are some other dimensions that are defined after this one. So the original VC dimension is for binary classification problem, for multi-valued functions, the functions that could be multi-labeled, is more than 2. There is another dimension, polar dimension for real valued function, stepping another step toward regression problem actually. Compared to the classification problem. And then the third thing, I will talk actually about these 2 more, but the third thing is you could change, I'm not really expert in this field, okay? I'm not sure if there is anything in the literature or not, but what you could do is that this is the definition that used for anything actually in this work. This is the misclassification, and the probability of this guy is the misclassification rate. So what you could do is that you could define some better distance metric, which is not just for misclassification. Probably in these 2 works, I didn't read actually these 2 works, but probably they have to change this definition to some other distance metric. Okay? For random variables, for instance, it's definitely much better to go for stochastic distance measures, like Kale divergence or these kind of things. and just put them instead of having this symmetric set difference. The third thing is beyond uniform learnable algorithms and having something problem specific. The problem here was that everything you need to use union bound to say what is the performance in the worst case, and then say that this is PAC learnable in the worst case even. But what would happen if you don't want to consider the worst case? In many situations you are not seeing the worst case in reality. The worst case over P, for instance, could be anything, right? And in many situations, you have a very small subset of possible probability measures on X and Y. That gives you problem-specific bounds, much tighter than whatever you have here. And then, of course, on top of that, you can add some finite time bounds, as you mentioned, for instance. So instead of having everything that could be somehow tight, or show the order of convergence once n goes to infinity, what could we say if n doesn't go to infinity? The true shape of that function, not just the shape of that function once n goes to infinity, something like that. And then this one, which we will see probably in later sessions, how to engineer samples. So here we didn't talk about engineering the samples. What we talked about was given a set of samples, what is the guarantee that you can give me on the learnability? Okay, but what you could do is to use those samples to somehow engineer the process of sampling, to take some more informative samples. So here, instead of assuming that the samples are giving to you from some distribution, stationary actually distribution should be, so some unknown but a stationary distribution on X and Y where you have some IID samples from, what you can do is that you can try to change the sampling policy here. So definitely you would have non-stationary distribution, but the number of samples that you need somehow to learn with that definition would be much smaller, of course. If you have a lot of samples in one region of that concept C, you don't need to have more samples there, right? So that was this. And then one thing that's good to look at is, does it affect the approximation error or estimation error, or both of them? What do you think? Here, I guess we can think about that. That is a good thing to think about that actually. Any idea? So you see the problem here. It's just
estimation error.
definitely it will improve estimation error, but what about the approximation error? It could improve actually approximations, and comes back actually to the very first slide, right? So what you can do really is that if you have something like this, then you can really change your hypothesis space. So after taking some samples, you have some information that tells you that the hypothesis space, the complexity of the hypothesis space is not of the right value. So you can change that, either increase that or reduce that. By increasing and reducing means that you can change to a completely different hypothesis space, okay? But you will dynamically change this hypothesis space, and since you are changing that, then you are changing the capacity of your estimator, which is somehow approximation error. So this is the capacity of your estimator kind of things, the best thing that you can get from this estimator. And this is the best thing in total that you could get, okay? So this is what you can do actually, which is not possible by this kind of works, because here the underlying assumption is the usual unsupervised learning setup, where the data set is given and you have no control on the new data set, okay? And then finally, generative classifier versus discriminative ones. And here everything is discriminative. And then what is the generative classifier? They try to learn P. So here what they're trying to learn, what we did was, we tried to learn H directly. So where is it? So we tried somehow to learn H, right? In generative models, they try to learn P. And from P, then once you give X, then they use usually Bayes rule or some modification of Bayes rule to tell you what is the most probable label for that very specific X. Okay? generative or discriminative. This is something that that would be very interesting also to work on. And some references, the PAC learnability paper. This is a very nice book by Vapnik where you can find everything about this VC dimension and lots of extensions of that. Sorry?
You have a book?
Yes, we have the book, and then you can get the book from KTH library, I guess.
Do you have a PDF?
Yes, this is a PDF. The quality of PDF is not that much great, but definitely readable.
You can send it there.
Sorry?
Can you see it?
Yeah, definitely. It's not a scan, like that's the point. So most of this is completely readable, very nice. But then there are some parts that is not that much readable. You can see that. I can share it with you. But you can download that from KTH server. The third one is a very nice paper, a little bit hard to read. Actually, the learnability and the VC dimension, and that was one of the references for this talk actually. And the last one is about these discriminative and generative classifiers. And they say that in many situations, generative classifiers, where you don't try to optimize over H directly, you will try to learn that mapping, that P distribution, joint distribution, and then try to infer some probabilistic H based on that, works better than this, which is very nice. That's it. Any question?
Just one small question.
Absolutely.
In VC dimension, you have the pre-assumption that target dimension is 2, right? You are
In
binary
the
class.
original VC dimension, yes, but then there are tons of extensions of that. So here you don't need to have just 2 labels. Here I can have n labels. And then it shows the capacity of your classifier when it is being applied for n labels. And then you can, for your works for instance, you can try to find this dimension for one specific class of neural network. And then it says that what is the actual capacity here? Something like that. Much better than considering the capacity or defining the capacity as the number of neurons or as the number of weights. Because the number of weights in a very deep network could be exactly like this, right? So the number of weights could be here, which could be infinite. Actually, this is not the number of weights. Actually, this is the number of weights, and for individual weight, you have infinite capacity there, right? Because this is a real value. Where the VC dimension or extension of VC dimension of that is much smaller. I know that there are some results for VC dimension of neural network, but just VC dimension, I know. Okay.